direction or the vertical direction. So the difference is, like a normal DFS, you'd be able to change directions, right? And so we start out with all these directions we can move. It's all the diagonals, all 4 diagonals in all 4 cardinal directions. And then once we get moving in one of those directions, we clamp that down to the single direction it's already going in. It's sort of moving like a queen would move. And so this is the canonical way to write a DFS with that one twist for the queen move style of search. And then part 2 is irrelevant for the purpose of this video, but my wife and I were thinking, like, we had this idea, like, how would you do it with a matrix? And so that's what I attempted to do in this script. And I'm not using Matplotlib, so I'll delete that. But basically, I'm using Torch for the tensor facilities and for the convolution facilities. And my first attempt here, we basically turn the graph that was given, the test example, we turn that into a tensor, and then we turn our kernel, which I created here, into a tensor. And this, by the way, this does not work. But I was attempting to, and I thought, yeah, I should use prime numbers. And so I tried that, and then we convert that to numbers, prime numbers, and now we can look at it, and it looks like, here, I'll do this, yeah. It's a list of numbers, and then we convert that to a tensor, and we can look at what it looks like now. So that's the input. I guess it's a 10 by 10 matrix. And then we have this kernel, which is all of the possibilities together. And I was thinking that it would work out, but I didn't do the mathematical proof, or like figure out the clever math needed to do it right. So this is just my failed exploration. Well, I guess it was a successful exploration because I disproved the theory that it would work. So it's a successful experiment. And then this conv2d, basically I'm passing in the whole 7 by 7 kernel of all the xmasses, and we're padding it by 3. So basically I'm moving this whole star around the whole other graph that was given our problem input. And something I discovered was, so I'm going to remove this truncate call, and we'll just look at the output here. Basically, when you create a conv2d, you have to set the bias to false, or else it'll add like a trainable bias to everything, to every output. So that's just me learning about neural network functions. And then this unsqueeze method on our image, we basically need it to be it's expecting, so it has this channel parameter. In channels, usually when you pass in an image, it's 3 channels. In our case, it's a single channel, but we still want to package it in a way where it looks like another channel. So the unsqueeze just adds another dimension to our image. And I guess I could try it without and see. Yeah, it doesn't like that. And it says that it expects 3D or 4D input. So when we unsqueeze this, and I guess we specify which dimension to unsqueeze, it creates the right shape. So we'll just do that here. I think if we look at it, compare the shapes, we'll see that it adds basically a channel dimension. And if it were a 3-channel image, that shape, the first one would be 3. But that's kind of irrelevant for this. I mean, it is relevant because it's what I spent the most time fiddling with, but it's irrelevant in the sense that it's not really the high-level idea, but it's what it took to execute it. And so that result, so if I search for the max of result, it says 595. And I guess that's just the highest concentration of, so like the center, that's the highest concentration of intersections of xmasses. But this result matrix is pretty mysterious now. So we've taken something very simple and made it way more complicated. And then I tried, so I guess what I tried that eventually worked, okay, this next attempt, what I did was I created 2 kernels, and then I read them in here, and we stick them in a list, turn them into tensors, and then go through and rotate them 90 degrees so we get all 8 styles of xmasses. And then if we look at a few of them, we'll see we just took our prime number thing and we're just like rotating it around. And the prime numbers aren't useful. They're just there for now. Well, I guess, no, I was thinking it would still work. So I passed in basically a stack. All right. So basically I say torch.stack kernels 8. And that gives me a kernels 8 tensor. It's all 8 kernels. They're 4x4 kernels and they're in a stack. And then we pass them into our weight data, because usually you would train this conv2D, but you can actually copy your own kernels in. And so that's what we're doing here. And this this has 8 output channels. So for each match, we will get a different channel. So for each kernel, it'll give us a different channel output. And then we simply sum the result And in the case of the test data, it does give us the correct answer. But when I put in the real data, it had an answer that was too high. And I think what was happening is we were getting too many interacting we're getting too many influences from the bigger data set of just like random coincidences adding up to the right amount, which is 87. If you take all these numbers and you square them and get the sum, it gives you 87. So, but we could also look at the result here, which is interesting, isn't it? So I had that bias problem here, so I'll just correct that so it's a little easier to see what this looks like. And this looks really big, so I wonder if we, it seems like our image is, I wonder if we have the data from our full input. So I'm just gonna look at the shape of this. Okay, so it is bigger because I added the padding of 3 to it. So it's gonna multiply all the way past the edge to capture, like if we have a kernel like this that needs to go all the way to the bottom, it's going to have an overlapping section. So I had to add padding so that it would catch everything. All right, so this didn't work because of the problem with the input data having too many coincidental sums that added up to 87. So what I did instead is I turned each kernel into a three-dimensional kernel. So I was doing two-dimensional, and that's what we see here. But the idea for the three-dimensional one is basically the X will go on its own layer, the M will go on its own layer, the A will go on its own layer, and the S will go on its own layer. And then we replace each one with a 1. And it might be confusing, and it was for me, that we're using a conv2D, but that really means that we're just like metaphorically moving the kernel around in two dimensions. So each channel, now basically we created a 4-dimensional image because we did that to the image too. So we have an image with just X's, an image with just M's, an image with just A's, and there's a stack of them. And so we're going to treat each of them differently. And so we have here a kernel that targets, or that layer of that kernel targets X's only, and then M's only, and then A's only, and then S's only. And I had to take care with this one because the dimension you stack on is important. So if I remove this call, it doesn't stack it in the right orientation. And we can look at this too. Let's just look at a couple of them. So for channel. So we can see that we have an X and then we have another X. And then we have an S and then we have another S. And it's not really clear, but if we add the dim equals 1 back in, we're going to see that things go in order. So you can kind of imagine like a 3D box, a stack of, I guess, layers that only look at their own layer of the image. And then in this example, you can see it's kind of diagonal, but it's diagonal in 3 dimensions. And then, so this one actually works. It gets the right answer on the example and on the real input. And I guess I annotated it for the purpose of this video, but basically in our hard work is happening basically in this stack, which has this tricky dimension variable. And our work is happening in this call to conv2d, where we have input 4 channels, out channels equals 8. And then our kernel size is 4 by 4. And I guess, right, so if we look at how people would describe this, they'll say like channels, or it'd be like batch channels height width, like that. And I think it's a little weird that I guess each kernel is independent in this case. If it were a 3D kernel, it would be a 4 by 4 by 4. So I guess that's the confusing part. And so basically for each channel, we have a 4 by 4 kernel. That makes sense. And our kernels line up here. And then we basically run the convolution on our image, and it gives us this answer, which is 18 on the example data. And then I've just visualized it here. And we can see in this area, this does have padding of 3, but there's a 2, which means there's 2 overlapping answers. And if we go up here to the top, we'll see, yeah, we can just verify it. It's kind of in this area, right? Xmas, and then, yeah, here it is. Here's the one of them, and then here's the other one, vertically. So, was it ridiculous to try? Yes. Did I learn a lot? Yes. And I think it was fun, a fun exploration. And I guess like if you have some crazy ideas, please put them in the comments, and we can all learn from one another. All right, that's it. Bye.